Now that you know the fundamental theorem of calculus, we can start to evaluate what's called indefinite integrals. And if you remember, the definite integrals had specific values. We had limits of integration there. And you thought of that as area under a curve. But now we're dealing with indefinite integrals, and so the answer to this is going to be a function. So basically we're looking for a function whose derivative is equal to that. Alright, so let's take this one piece at a time. What's the antiderivative of 1 over x cubed? Well, think of 1 over x cubed as x to the negative third power. So with the power rule, we know when we take the derivative, the exponent goes down by 1, or we subtract 1 from the exponent. So to go the reverse way, we would need to add 1 to the exponent. So we know that we're going to have negative 3 plus 1 is going to be negative 2. So our antiderivative is going to look something like x to the negative 2. Now what we have to do here is let's differentiate this and see what we get. What's the derivative of x to the negative second power? Well, using the power rule, that'll be negative 2x to the negative third. Or another way of saying that is negative 2 over x cubed. But that's not what we had to start with. We didn't have the negative 2. But that's okay. If it's just a constant that's the difference between what we have, then we can fix that. So what we can do is multiply our answer by negative 1/2. And now, when you take the derivative of that, negative 1/2 x to the negative second, you're going to multiply negative 2 times negative 1/2, which gives you a positive 1, and then x, and then we subtract 1 from the exponent, and we get 1 over x cubed. So we've got that. Alright, let's work on the next term, e to the x. Well, that's an easy one because the derivative of e to the x is e to the x. So that one's done. Alright, let's look at the square root of x. Now we want to think of that as x to the 1/2 power. So before we took the derivative, the exponent should have been 1 higher than that. So if I add 1 to that, I'm going to get x to the 3/2 power. But if I take the derivative of x to the 3/2 power, I get 3/2 x, and then when I subtract 1, I have 1/2 power. That's close to what we need, except we don't need the 3/2. So I need to offset that with the reciprocal 2/3. So now when I take the derivative, I just get x to the 1/2. So we're going to have plus 2/3 x to the 3/2 power. And once again, take the derivative of that just to check. Alright, and finally, what function has a derivative equal to negative sine x? Oh, that's just the cosine of x. Remember, derivative of cosine is negative sine x. Now we could also have any constant added on to all of these, because the derivative of a constant is 0. So when I take the derivative of this, it doesn't matter what the constant is, that'll become 0. So here is the antiderivative, or the integral of 1 over x cubed minus e to the x plus the square root of x minus sine of x dx. Alright, let's try another one. And it's a good idea for you to hit pause and try and do this on your own first, and then compare with the answer. Okay, this one's a tough one, and I'm guessing if we were in class and I was asking people, we'd get a lot of different answers, but then when I would take the derivative of these answers, I wouldn't get this. So we have a little bit of an issue here. So here's where you have to recognize something. I've got two functions multiplied together plus two functions multiplied together. Maybe that would trigger, if you've done enough differentiation, maybe that would trigger something that reminds you of this. U prime v plus uv prime. That's right, the product rule. So are there two functions multiplied together that when you take their derivative, you would get this? How about e to the x sine x? Now if I do let's check this. Let's do the derivative of this. The derivative of e to the x is e to the x times the second function plus the first function, which is e to the x, times the derivative of the second function, which is cosine of x. And that indeed is what we started with. So I know this gets frustrating at times, plus any constant, because it seems like there's no certain way we approach these problems. And so that leads us to the main idea I want you to remember about integrals. Differentiating was fairly easy. We had rules to follow. We looked at a problem, we decided which rule to use. Integration, on the other hand, is not like that at all. I say it's more like an art form, and you just have to practice. And you recognize things like that last example, the product rule, the more you work with them. The more you take derivatives, and you're familiar with how to differentiate, the easier it is to figure out how to work backwards and do integration. So I have a couple examples to work through. And once again, you might want to try them on your own first, and then go ahead and hit play and see how you did. Alright, so let's find the integral of 3x plus 2 over x quantity squared. Well, this doesn't look so easy. And you might think, well, maybe it should be 3x plus 2 over x to the third power, because the exponent here was 2, and so we add 1 to that and we get 3. Well, what if we take the derivative of this? First we would do 3 times the quantity to the second power. So far that looks pretty good. I mean, the 3 doesn't look good, but we could always throw 1/3 in front. But then we have the chain rule, and we have to multiply by the derivative of the inside, which is going to be 3 minus 2 over x squared. And that's not even close to what we had started with. So this isn't going to really work for us. It's a little too complicated than just having a power rule solution. So what we want to do is ask, is there another way we can write this expression? Well, sure, let's square it. Let's multiply 3x plus 2 over x times itself and see if that's an easier form to work with. When we multiply that out, we're going to get 9x squared. And then we're going to get 6 plus 6 is plus 12. And then plus 4 over x squared. So when you multiply these two terms, the x's will cancel and you just get 6. And the same thing here. So that'll give 6 plus 6 is where I got the 12 from. Alright. Now, let's take the antiderivative of each part. We have 9x squared. Well, we know that it's going to be something x cubed. When I take the derivative of x cubed, it becomes 3x squared. And I want 9x squared. So if I have another 3 here, now when I take the derivative, it'll be 9x squared. Alright, 12. Well, that's easy. That's just 12x. The derivative of 12x is 12. And then the last one, let's think of it as 4x to the negative second power. So I'm going to add 1 to the exponent, which would make it 4x to the negative first power. And when I differentiate this to check, this derivative would be negative 4x to the negative second power. That's close, but I don't want the negative. So if I had a negative here, then those negatives would cancel out. So we're going to say minus 4x to the negative first, or just minus 4 over x. And then don't forget, plus any constant. There's a whole family of functions whose derivative equals that integrand. So don't forget that you're getting a family of functions for a solution. Alright, let's try another one. How are we going to handle this? Now I know some of you might have thought of the second problem in the opener and said, well, wait a minute, maybe this reminds me of the quotient rule. And you could work with that for a while, because remember, the derivative of u over v is equal to u prime v minus uv prime over v squared. But I think after a little bit of trial and error, you're going to have difficulty coming up with a solution for this. And in the numerator, notice we don't have two functions subtracted from each other. We just have single functions. So that's not going to work. So the next question is, well, this is pretty complicated. Is there a different form we can write this as? So what if we took this and broke it into two fractions? And we had x squared over the square root of x, or x squared over x to the 1/2, minus 2 over x to the 1/2, or 2x to the negative 1/2 power. Now, what do you do when you have a variable to a power over the same variable to another power? Well, when we divide, remember back in algebra, like x to the 5th over x squared, that's x to the 5 minus 2. So you just subtract the exponents. So 2 minus 1/2 is 3/2. So that simplifies to just x to the 3/2 minus 2x to the negative 1/2. Alright, so let's take these one piece at a time. X to the 3/2. Well, if I add 1 to the exponent to anti-differentiate, that's going to become x to the 5/2. But when I take the derivative of that, I don't have a 5/2 in front. So if I multiply it by a 2/5, now when I take the derivative, I multiply 5/2 times 2/5, which is 1, and then x to the 3/2 power. So that's what I want. So I have 2/5 x to the 5/2. Alright, let's try the next one. I have negative 2x to the negative 1/2 power. So don't concern yourself too much with the constants in front. Let's first of all figure out the power rule. If I add 1 to the exponent, negative 1/2 plus 1 gives me x to the 1/2 power. Now when I take the derivative of x to the 1/2 power, I get 1/2 x to the negative 1/2 power. So let me offset that exponent 1/2 with a 2 over 1. And let me also remember that I had a negative 2 in front. Now let's see what happens here. When I take the derivative of this, it's going to be 1/2 times negative 4, which gives me a negative 2. And then I subtract 1 from the exponent, I get x to the negative 1/2. So this is negative 4x to the 1/2 power. So minus 4x to the 1/2. And plus any constant. And once again, when you think you're finished, it's always a good idea to take the derivative of your answer and make sure you get what you started with, maybe just in a different form. Alright, let's try one last one. The integral of x cubed times the square root of x plus 1 over cosine square root of x. Alright, so if you haven't figured out by now, when you can rewrite anything in a simpler form, that's going to be the way to go. So how about x to the 3rd power times x to the 1/2? Well, let's just add those together, and we get x to the 3.5, or 7/2 power. Now this 1 over cosine squared looks kind of complicated. But wait a minute, isn't the reciprocal of cosine secant? So that's really just saying secant squared of x. Okay, so what's the antiderivative of x to the 7/2? Well, if I add 1, that becomes x to the 9/2. But when I take the derivative, I don't want that 9/2 in front, so I'm going to offset the 9/2 with a 2/9. Now when you differentiate that, you'll get 1x to the 7/2. And what about secant squared? Well, if you remember your derivatives, the derivative of tangent is secant squared. So that's just tangent of x. And once again, don't forget plus any constant. So those family of functions all have the derivative equal to x to the 7 halves plus secant squared x. Okay, your assignment, 18D, page 455. And take your time, work through those, check your answers as you go, and let me know if you have any problems.